I want to talk today about a lesser-known phenomenon in electricity, the phenomenon of parametric resonance. I came across this effect many years ago in a paper from the 1930s, entitled On the Parametric Excitation of Electrical Oscillations. I only vaguely understood the concept at the time, but years later I was returned to the subject while watching a lecture by Eric Dollard. For those who don't know Eric Dollard, he is an electrical engineer with a background beginning in naval engineering, continuing on as a radio engineer for Bell Labs, and eventually working independently to replicate the work of Nikola Tesla and other scientists of electrical antiquity, and later would devote his life and time to creating books and lectures to elucidate and preserve information on the history of electrical development, the theories which led to these developments, and experiments and effects which have been overlooked or forgotten through time. Eric Dollard still produces lectures and conducts many experiments to this day. It was in his lecture, The Origins of Energy Synthesis, which I had watched tens of times over many years, that something he said struck me that hadn't in all those times before.
Steinmetz began study of what's called synchronous parameter variation. The meaning of this is the variation of energy storage coefficients, such as inductance or capacitance or resistance, with respect to a point in time on the AC cycle. Now the normally constant or time-invariant coefficients change in value with respect to time. Now we have a peculiar set of dimensions of henries per seconds, ohms per seconds, farads per seconds, and Siemens per seconds, and this is where the concept of the law of conservation of energy comes apart, because the energy is appearing and disappearing in these relationships without any equality or connection anymore. Energy could either vanish or energy could appear in the system.
Charles Steinmetz, who Eric is referring to here, writes about this effect in his book Theory of Alternating Current Phenomena. In this chapter, Steinmetz talks about the parametric variation of inductance naturally taking place in the armature of very large generators. Steinmetz shows that this parametric variation has the effect of either consuming or generating power in the system. The combination of Dollard's lecture in this chapter from Steinmetz's book reminded me of that paper I had read and saved many years before. When I brought up the paper and read it this time, the function of this effect became very clear to me, and I was sure that it was a subject worthy of further investigation. Before we talk about the theory and experimental setup of parametric resonance in electric circuits, I'd like to start with an introduction into mechanical and electric oscillators in their basic form. One of the most simple examples of a mechanical oscillator is a spring and mass system. This equation describes the motion of the mass in terms of the position x. V is the velocity, and a is the acceleration of the mass. These both can be written as the first and second time derivatives of the position, respectively. The displacement x, the mass m, and the spring constant k determine the motion of the mass and spring. B is the damping coefficient, which accounts for the loss of energy due to resistance in the system, such as friction or air drag. For now, we will ignore the losses, so this term can be dropped from the equation. Rewriting this equation, we get the familiar equation F equals ma, where the force F equals negative kx. Rearranging the equation, we arrive at this form. We've already stated that the acceleration is the second time derivative of the displacement, and it turns out that the frequency of oscillation of the system is the square root of the ratio of the spring constant to the mass. Squaring both sides, we can now substitute for A and K over M to arrive at our equation for a simple harmonic oscillator. We can see that the solution of X must be a sine function containing omega t, because its second derivative would be negative omega squared times sine omega t, like we see on the right-hand side. A similar example of a simple harmonic oscillator is the pendulum. The equation is nearly identical, besides the sine term, which is necessary to account for the circular path of the pendulum, and the displacement is in terms of the angle theta instead of the linear position x. Here, the motion of the pendulum is determined by the displacement angle theta, the length of the pendulum L, and the gravitational constant g. For small angles, the sine term can be dropped, and again ignoring the losses, we arrive at this equation. Substituting in a similar fashion, we arrive at a symmetrical equation to the spring and mass system. The most important part to take away is that the oscillation requires two stores of energy to exchange the energy back and forth. Also, note that the frequency of oscillation is related to the ratio of these two energy storage coefficients. Moving to electrical oscillators, we'll look at a circuit with an inductor, capacitor, and resistor in series. By Kirchhoff's law, we write that the voltages across each element must sum to 0. Writing the voltages in terms of the electric charge Q, we reveal three coefficients, L, R, and C. L is called the inductance, which represents the ability to store energy in the magnetic field of the inductor. C is called the capacitance, which represents the ability to store energy in the electrostatic field of the capacitor. And R is called the resistance, which represents the ability to drain the electric energy stored in the circuit by converting the electric energy into mechanical energy as heat, thereby representing the energy loss in the system. The current I, which must be constant through all the elements in the series circuit, is equal to the time derivative of the charge, Q, and so the equation can also be written in terms of I. But for symmetry's sake, we will keep our equation in terms of Q. Ignoring the losses and dividing by L, we see the relation of the charge Q to its second derivative. The resonant frequency of an inductor and a capacitor in series is given by this equation, and after squaring both sides, we can substitute to arrive at the equation for our electric oscillator. It's interesting to note the difference, how the mechanical oscillators are quantified by their spatial displacement from equilibrium, whereas the electrical oscillators are quantified by their electrical displacement from equilibrium, the charge Q. The real-life example of this circuit is a coil of wire, which is good at storing energy in its magnetic field, and a capacitor, which is good at storing energy in its electrostatic field. Here is a more practical example with smaller components. Now let's look at a graphical representation of our series resonant circuit. If we charge the capacitor to some voltage with the circuit open, we can see what happens when we close the circuit and the oscillation begins. The energy stored in the electrostatic field transfers into the magnetic field, and at the end of the transfer, all the energy which was stored in the capacitor is now stored in the inductor. Now the energy is returned from the inductor to the capacitor, and all the energy is stored in the electrostatic field once again. This energy exchange continues back and forth forever, since there is no energy lost in the system. Now accounting for the losses, we add a resistor to our circuit. Now we'll see what happens in our resonant circuit when the losses are included. Charging the capacitor and closing the circuit, we can see an exponential decay of the energy in the system. This exponential decay is given by this equation, which is determined by what is called the Q factor of the circuit, which is relational to LC and R, and by the angular frequency of the oscillation omega. With this basic understanding of the series resonant circuit, we are ready to look at the phenomenon of parametric resonance. Here are the equations for the energy stored by the magnetic field, W sub L, and the electrostatic field, W sub C. We will charge our capacitor and let the energy transfer through an initial inductance, which we'll call L negative delta. At the end of the energy transfer, we know that all the energy in the capacitor must now be stored in the inductor. That is, after the transfer, W sub L must equal the initial W sub C. At this moment in the cycle, we increase the inductance of our coil by some means to a greater value L delta, effectively increasing the stored energy as W sub L is proportional to L. We now allow this greater energy to transfer back into the capacitor. Since W sub C must equal W sub L at the end of the transfer, there will be more energy stored in the capacitor than there was at the beginning of the cycle. Returning L to its original value, we can repeat this process. The now larger W sub C transfers into W sub L, and we again change the inductance to L delta, increasing the stored energy again. The inductor transfers the energy back to the capacitor again, resulting in an even higher W sub C, and the full cycle is complete. We know that L is relational to the frequency of oscillation in the way that when L is lower, the frequency is higher, and when L is higher, the frequency is lower. To make up for this distortion in the sine wave of the oscillation, the inductance must be varied at a frequency relational to the average inductance of L negative delta and L delta. We can also see that the frequency of parameter variation of L must be twice the average resonant frequency of the oscillation. Even though we've used a square wave variation of L for an easier understanding, L may vary sinusoidally and obtain much the same effect, since L is still increased during the discharge of the inductor into the capacitor. Looking at the math of this parametric oscillator, we return to our original equation for the series LCR circuit. Now L varies sinusoidally with an amplitude m. As we saw, omega p is twice the average resonant frequency omega r. Multiplying through by L naught, we can write L naught times m as L delta. Removing the resistance term and multiplying through by Q double dot, we get the equation of a driven oscillator. That is, an oscillator being driven by some source of power. We can see the direct similarity to the equation of a mechanical driven oscillator, where F is the driving force. And looking at the equation for an electrical driven oscillator, where Vd is the driving voltage source, we notice they are identical. Since we know Q double dot is the derivative of current, and we showed that varying L in this way leads to higher current each cycle, the driving force will in turn be greater each cycle, and the oscillations will grow to infinity. Including the losses, we obtain the equation for our parametric oscillator. Here is a real-life example of our parametric oscillator circuit. We have our variable inductor, delta L, and a capacitor bank, C. The way the variable inductor works is by passing a toothed disc of copper between pairs of series-connected coils. When the copper is in between the coils, the inductance is lower. And when there is just air between the coils, the inductance is higher. As the disc spins, the inductance will vary sinusoidally. Now we'll look at the graphical representation of our electrical parametric oscillator. Adding our variable inductor into the circuit, the capacitor only needs a minuscule amount of latent charge, as even any dead capacitor will have some latent charge. The process of exponential growth begins, and after a short amount of time, the current begins to take off. And since the current must be constant through all the elements, we see that the voltage across the resistor takes off as well. This means that real power is being generated in the system, and is able to do real work, creating heat through the resistor. Seeing on the right the equation for the energy gained per cycle by the change in inductance, and the equation for the energy lost per cycle through the resistance, the condition where the oscillations go to infinity is given by this inequality. That is, the energy gained due to the change in inductance per cycle must be greater than the energy lost to the resistance per cycle. Looking closer at the inequality, we can simplify by dividing each side by a half and by I squared to get the very simple relation delta L greater than RT, where T is equal to the time of a quarter period. Using the values from the previous example, we get a resonant frequency of about 1027 Hz, which gives a period of nearly 1 millisecond. Dividing by 4 gives T, the time interval of energy exchange. Finally, plugging in and solving for R, we get about 165 ohms. Starting with a resistance above 165 ohms, we can see that the oscillation exponentially decays as more energy is lost than gained per cycle. As we drop the resistance below 165 ohms, the oscillation grows exponentially as more energy is gained than is lost per cycle. And as we hone in on 165 ohms, we see the tipping point for the condition of parametric resonance to occur. Thank you all for watching, and thank you to this year's Summer of Math Exposition for inspiring me to make this video. I will definitely be making more videos in the future, looking deeper into this subject and many more.
Before the Steinmetz method, engineers had used differential equations or graphics to calculate alternating current problems. With all the mathematical baggage aside, engineers could see the alternating electric wave with crystal clarity. In this view, a few engineers knew that electrical energy can be synthesized, literally created along certain lines of mathematical reasoning. At a lecture of the American Institute of Electrical Engineers, in which Steinmetz, Tesla, and others threw their ideas back and forth about these, Professor William Anthony stated at the closing of the meeting that within 1 year they were going to have a self-sustaining electrical system that didn't need any fuel. This was in the 1890s. Where is it today?